All right, we are ahead of the syllabus by a couple of lectures at this point, and since the first exam is coming up, it seemed to me better to spend the extra time we have going over homeworkish and exam-like problems rather than presenting new material. So for this lecture, I'm just going to go over the examples to the practice exam. If you want to do the practice exam before you see what the answers are, and I highly recommend that, then don't watch this until after you've done the practice exam. I'll post the practice exam on Monday, and then you can just put this lecture in the bank until after you've done it yourself, and then look and see that you got the answers right, but also that you understand how each of the problems is done. I should say that or emphasize, I guess, that the first part of this practice exam is in fact the actual exam 1 from 2 years ago. So very representative of what exam 1 will be like this time as well. So with that, let's start. I don't know how long it will take to go through this. I intend to go through it slowly and carefully. If it gets to be too long, I'll break it up into several pieces. So problem number 1 is an anthology of several small problems, the first one of which is 1 mole of a solid melts at constant pressure of 10 atmospheres and constant temperature of 500 K. The molar enthalpy change for the process is delta HM, delta H per mole that is, of 40 kilojoules per mole. What is the molar entropy change for the phase transition? I have some extra space that I've given myself over here on the right-hand side, left-hand side. But I don't think I need it for this particular problem. This is a particularly easy one. So it's a constant temperature process, which means that the entropy change is the heat change divided by T. And the heat change in this case, it's happening at constant pressure, so this is a QP. And the heat change is the enthalpy of melting, so delta H per mole for melting divided by T. That's 40,000. Always remember to change kilojoules to joules. I occasionally forget to do that myself. Divided by the temperature, which is 500 K. And that is equal to, let's see, 400 divided by 5, that's 80 joules per K. That one was easy enough. Part B says, if a system has 5 possible quantum states, and the probabilities for states 1, 2, 3, and 4 are 0.4, 0.3, 0.1, and 0.1, what is the probability for of P5 for state 5? This relies on the fact that the sum of all the probabilities for any system have to add up to 1. And that's true no matter how many states there are, no matter how many terms there are in this sum. So we know 4 of the 5, that means P5 is equal to 1 minus all the others, in this case P1 plus P2 plus P3 plus P4. And that is equal to 1 minus P1 is 0.4, P2 is 0.3, and P1 and P2 are both 0.1. All of that adds up to 0.9, and so the probability for P5 is 0.1. Part C. A system undergoes a reversible change at a constant temperature of 300 K. The total energy change is 100 kilojoules and the work is minus 50 kilojoules. What is the entropy change for the process? So constant temperature, again, that means delta S is again equal to Q over T. We need Q in order to do that calculation. We have delta U, which is Q plus W, and we have W and we have U, so we can get Q. Delta Q is equal to delta U minus W, which is 100 kilojoules, minus a minus 50 kilojoules, which is 150 kilojoules. Therefore, delta S is equal to 150,000 divided by 300K and that is equal to, I think, 500 joules per K. Is that right? Let's see. 1500 divided by 3. Yes, 500 joules per K. Part D. 100 milliliters of a liquid with a heat capacity of 200 joules per K is heated at constant pressure of 10 atmospheres from 300 to 350. What is the heat exchange for the process? So this is just a simple, so it's constant pressure, so we need a CP. It doesn't say what the heat capacity is, whether it's a CP or a CV, but it's a liquid, which means that there's very little volume change in the course of the warming. Only the thermal expansion, which is for liquids, is really small. And so the heat capacity for CV and CP are essentially the same, and so we'll just use it that way, assuming that it's close enough to the constant pressure heat capacity for our purposes. In that case, Q is equal to CP times delta T. That's 200 joules per K times a delta T of 50K plus 50K. Notice it went up from 300 to 350, and that is 10,000 joules or 10 kilojoules. All right, those were pretty straightforward. Let's go on to number 2. The thermodynamic data for this is at the end of the exam. So there's a fairly extensive table of thermodynamic data at the end of the exam. There are also a number of other constants there, so if you seem to be missing some information that you need for the problem, look at the end of the exam, see if it's there. I'm pretty sure that I have put into the exam everything you'll need, so if you seem to be missing something, probably it's at the end. All right, so we have a reaction, 2 COs plus an O2 goes to 2 CO2s. Find the values of delta H reaction and delta S reaction at 298. So what we need are the values from the table. Notice that the values we need are all for gaseous compounds or gaseous species, and we will need delta H, we will need delta S, and eventually, since it's asking down here for these quantities at a different temperature, we're going to need the heat capacity data as well. So for CO, CO2, and CO2, let's look down at the bottom. Here we are. So we need CO, there it is. We need CO2, and we need O2. Where is O2? There it is. All right, so let me see if there's a way, well, I'll just have to copy them up, I guess. So CO is minus 110.53 and 197.6. Here I can do this. Minus, there we see. So bookmark that, and bookmark that, and then look only at bookmarks. So minus 110.53 and 197.6. Minus 110.53 and 197.6. And the heat capacity data are also down here. They're in a different table. So for CO 29.0. Now for O2, O2 is an element. The delta H for any element is 0. The delta S is not 0 though. And so that is 205.0, and the heat capacity for O2 is 29.4. For CO2, the delta H is minus 393.51. The delta S is 213.6, and the heat capacity is 36.5. All right, so those are the raw data that we need. Now let's calculate delta H. That's products minus reactants weighted by stoichiometric coefficients. So it's 2 times the CO2 value minus 393.51 minus the C2 times the CO value minus 110.53 plus the O2 value, which is 0, and that is equal to 2 times minus 393.51 minus 2 times minus 110.53, and the 0 we don't have to put in, and that is minus 565.96. And then delta S is equal to 2 times 213.6 minus 2 times 197.6 plus 205.0, and that is 2 times 219.6 minus 2 times 197.6 plus 205. And that is, oh crap. Minus 161. Period. Let me make sure that that's really right. I think that's right. Yeah, okay, so minus 161 joules per K. All right, so those are our two answers for the first part. Now we have to use Kirchhoff's rules to calculate those same numbers at a different temperature. Kirchhoff's rules are delta H is equal to delta H0, which is what these guys are, the standard state value, plus RT plus C, delta CP, times delta T, and for delta S, it's delta S plus delta CP log T2 over T1. Delta T is 298 goes to 348, so that's 50 Kelvin. And so delta H is then equal to minus 565,960, right, in joules, plus delta CP, but we haven't calculated delta CP. Let's do that. Delta CP is equal to 2 times the 1 for CO2 here, 36.5, minus 2 times the 1 for CO, 29.0, plus the 1 for O2, 29.4, and that is equal to 2 times 36.5 minus 2 times 29 plus 29.4, and that is equal to minus 14.4 joules per K. So in here goes minus 14.4, and then delta T is 50, and so our number is minus 565,960 plus minus 14.4 times 50, and that is equal to minus 566,680. All right, so minus 566,680 for delta H. Delta S, delta H. Delta S is then minus 161 plus minus 14.4 log of 348 over 298, which is equal to, so that's the same as this, let's undo here, except log of 348 over 298. Oops, no, sorry. Also have to change that. So minus 163.23. Okay, so that's a straightforward Kirchhoff law problem. I think I will stop now after doing those two problems. They were fairly long, and I'll do another lecture for the next problem.